Epistemic temporal logic and infinite games both deal with the same kind of notions, which are action, knowledge, and time. So on the one hand, epistemic temporal logic can express explicitly statements which are combinations of action, knowledge, and time. And on the other hand, game theory deals with concepts, notions, such as observation-based strategies, which are implicit combinations of action, knowledge, and time. So the objective of this work is to formalize the results and the notions of infinite games in terms of statements of epistemic temporal logic involving the notions of action, knowledge, and time. So how will we do this? We will proceed by splitting up the embedding in two embeddings and resorting to supervisory control theory. So the first part will consist in embedding infinite safety games into supervisory control theory. And the second part will consist in embedding supervisory control theory into epistemic temporal logic. And via these two embeddings, we will be able to obtain the embedding of infinite safety games into epistemic temporal logic. So I forgot to mention that we will only consider infinite games with safety objectives. Is there a way to point? No? Okay. So what will be our contributions? There will be yes. And for point. Okay. Thank you. So there will be several contributions. The first will be to have the possibility to determine whether there exists a winning strategy in a given state, instead of having to construct all the winning states from the beginning of the game. The second will be to have the possibility to synthesize all the strategies on the fly, instead of having to synthesize them before the beginning of the game. That is on the fly, meaning after a sequence of events, the players can determine whether or not they should play an action such that this action will stay within a winning strategy. The third contribution will be to have a reformulation of the main notions underlying infinite games in intuitive terms. This will highlight the intuitions underlying these notions of game theory. And what is important to stress is that all our results will be expressed in terms of model checking problems of epistemic temporal logic. And this reformulation in this format will allow us to have the possibility to use model checkers for epistemic temporal logic such as MCMS or MCK. So the talk is structured as follows. I will first present the three ingredients: control theory, epistemic temporal logic, and infinite games. Then I will present the first embedding from supervisory control theory to epistemic temporal logic. Then I will present the second embedding from infinite games to supervisory control theory. And finally, thanks to these two embeddings, I will be able to present the main results, which are the reformulation of imperfect information games and perfect information games in terms of model checking problems in an epistemic temporal logic. So I start with supervisory control theory. Maybe that's the theory that most of you are the less aware of. So the setting is as follows. You have two ingredients, the plant and the objective. The plant represents and models the behavior of the system itself. It's usually a deterministic transition system. And the objective is also a deterministic transition system, which is also represented by a language K. So K will denote the objective, and L of A will denote the behavior of the plant, of the system itself. So the control problems can be stated as follows. There are two kinds. First is the supervisor existence. Does there exist a supervisor that can control the behavior of the plant so that we can realize fully the goal objective? And the supervisor synthesis is in the case where such a supervisor exists, how can we synthesize it? Or how can we build it in a way or another? So as we will see, sometimes it's not possible to realize exactly the goal behavior. So in that case, what we would want is to have a supervisor which stays within the goal behavior. And which stays within the goal behavior not only trivially, but also which stays in the goal behavior so that he realizes as much as possible of the goal behavior. Yes?
This assumption that the plant is deterministic, how critical is it? Is it just convention or is it important to the behavior?
I would say...
or it comes to the results, is it harder to control?
Well, I believe if it's not deterministic, you may use partial observation techniques to deal with non-deterministic.
Yes, maybe, but for some of the results, yes, it plays a role because you need to have some kind of some kind of determinism. So I don't know how these results can be adapted, but of course you can do a process construction and avoid the determinism. But yes, for some of the results, it does play a role. But yeah.
The arenas for your site, you consider this deterministic arena.
No, on the game side, it's non-deterministic. That's one of the main differences. No, it's non-deterministic. And that's why we need to introduce this, I will show it later, that's why we need to introduce this unobservable events.
Okay, no, I meant perfect information. You can consider it deterministic, no?
No, it's non-deterministic as well.
We'll see.
We'll see, yeah. So what is a supervisor? It's a function which goes from a set of sequence, which goes from the behavior of the plant to a set of possible events, and these events are the events which should not be disabled by the supervisor after the sequence of event W has occurred. So among these events, there are a set of controllable events and a set of uncontrollable events. And of course, all the uncontrollable events should not be disabled by the supervisor because he cannot control them anyway. So this supervisor, this function, gives rise to a controlled behavior, or supervised behavior, which will include all the sequence of events which are allowed by the supervisor. So it's defined inductively as follows. First, there is the empty word, and then a sequence of events W sigma belongs to the control behavior. If W already belongs to the control behavior, sigma is not disabled by the supervisor, and W sigma is indeed allowed by the plant, by the system. Okay? So this way we build all the sequence of events which are allowed by the supervisor. But of course, then now the problem is to be able to control this plant so that we realize the Gore behavior K. And this can happen only if this condition holds. If and only this condition holds. And this condition says that if you are already within the Gore behavior, after the occurrence of any uncontrollable events in the plant, you will still stay in the Gore behavior. Okay? So as you can see, all these conditions about the plant and the Gore behavior are expressed in terms of intersection, inclusion, concatenation of languages. And our goal will be to reformulate these results in terms of model checking problems in an epistemic temporal logic. So now comes a setting which is a bit more complicated, in which you have imperfect information. In that case, some of the events are non-observable. So we first define a projection, P, on the sequence of events to the sequence of observable events, naturally as follows. And what we call a P supervisor is a supervisor which is an invariant under a sequence of events which have the same projections. Okay? Which is some kind of equivalent of observation-based strategies, as we will see. And now we need another condition to be able to realize exactly the Gore behavior. And this condition is the condition of observability, which reads as follows. So, as you can see, it's not so easy to read it, huh? And it's it's a bit complicated, but hopefully, maybe with the epistemic temporal logic approach, it will be easier to grasp it. But the point is that by adding this property, this notion of observability, to the notion of controllability, then we have a necessary and sufficient condition for the realization of a supervisor, a P supervisor, which can realize exactly the Gore behavior. So now comes the epistemic temporal logic part. So we are going to take our plant, our Gore behavior, and we are going to build a new transition system which models the behavior of the system, the whole system. So it's just a synchronous product of the plant and the Gore behavior, the Gore automaton. So the states are just the Cartesian product of the states of the plant and the states of the Gore behavior. The transition system is just defined as follows. So in case only one of the transition is defined, then the other ones goes to a sync state. The new initial state is this one. And we have a labeling function which assigns PLM to states which belong to the final states of the automaton, the plant, or the plant. And we assign PK to the states which belong to the final states of the Gore behavior. So now we can define the interpreted system which is associated to this environment. So to each word, to each infinite word of which is in the behavior of this environment, we associate a run, which is defined as follows. So first we have R0, which is just the sequence of new symbols. And then it's inductively, when there is an event, for example, then sigma 0 occurs. Sigma 0 is mentioned here, is in the environment, the local state of the environment. And all the other processes, what they perceive depends on whether or not this event sigma m belongs to their set of events which they can observe. If they can observe sigma m, in our case sigma 0, then they will add it to their local state. Otherwise, they will just stay with their previous observation, which was sigma mi. Okay? And we assume that agents have perfect recall. And we define the valuation by putting the valuation corresponding to the state that we have reached after the sequence of events sigma 0 to sigma n, plus p sigma m, meaning that the event sigma m has just occurred. So p sigma m means when it's true in a global state, such as this thing here, it means that the event sigma n has just occurred. So some notations. Ri of m denotes the is component of the global state R of m. So R of m is just a tuple, as we saw before. So R of m is something like this. So here is R of m plus 1. And Ri of m plus 1 would be the is component here. And two global states, 2 points R of m, R prime of m prime are indistinguishable for agent I, where their local states, I of m, are equal. So here it should be I. And to each word we can associate a run naturally as before, even when it's finite. So now we can define the syntax of our logical language. So it's just the temporal logic. I forgot the universal and the existential quantifier. Sorry. There is also the for all and there exists. And there is also the knowledge operator and the distributed knowledge operator. So we will not use it in this talk, but if we have time, I can talk to you about it at the end. We have the eventually modality, the always modality, and this modality is a counterpart of the PDL modality after the event sigma phi holds. And the dual is this one. And we also have this abbreviation, which looks quite complicated, but whose intuitive meaning is quite simple. It says that the current state is safe, and after the occurrence of any finite sequence of uncontrollable events, we will still be in a safe state. Okay? And this until is the dual of the until. That is not phi until not psi. So the truth conditions are as follows. So P proposition letters if they belong to the labeling function. Not phi, conjunction, next, until, it's all standard. Also for the existential quantifier. And for the knowledge, it reads as agent I knows phi in IRM if only for all the runs R prime and the points M prime, which are indistinguishable for agent I, phi holds. Okay? So he knows phi when in all the runs which are indistinguishable for him, phi holds. Now some notations. So I'll go quickly through them. Maybe the important one is this one because we will use it later on a lot. It says that after a sequence of events represented by W phi holds, if only if in all the runs which are the continuation of the word W, phi holds. And here is just standard notation for in case we deal with a state, not a sequence of events. So the model checking problem of this logic was not known because it has an asynchronous semantics. It's not a synchronous semantics. And it turns out to be k epistime, where k is the attenuation depth of the formula. Okay. So There is a subsection infinite games, but I will not talk about it. I'll talk about it later. So now I will reformulate the different notions of controllability and observability in this epistemic temporal logic. So I start with the notion of controllability, and the expression that we saw before is formalized in our epistemic temporal logic by this model checking problem. So when you are in a safe state, then after the occurrence of any finite sequence of unobservable events, uncontrollable events, the supervisor is still in a safe state. Okay? And if this condition holds, then there exists a supervisor F which can realize exactly the goal behavior. And conversely, if there is a supervisor which can realize conversely the goal behavior, then this condition must hold. And how do we synthesize the supervisor? We synthesize by a model checking problem as follows. So, of course, it should contain all the uncontrollable events. It should also contain the controllable events such that after the sequence of event W and after sigma, if sigma can occur, then we are still in a safe state. Okay? So that's how we build the supervisor. It's defined by a model checking problem like this one. And as you can see, we do not build the supervisor before the beginning of the game and fully. We can just build it online by checking after each sequence of event W whether sigma can be enabled. So now we move to the setting of imperfect information. And in that case, the notion of observability corresponds to these two equivalent notions. And as you remember before, it was a bit complex to understand what this condition of observability meant. But actually, when you read this formula, it makes sense. Because it says that if the system is in a safe state, the event sigma can occur, and after the event sigma, we are not in a safe state, then the supervisor knows that after sigma, the system will not be in a safe state. Okay? And this condition of observability, if we add it to the condition of controllability, then we have a necessary and sufficient condition for the exact realization of the goal behavior. And again, the supervisor is defined by model checking problems. That is, an event is not disabled by the supervisor after the sequence of event W, if only if either it's an event he cannot control, or if he can control it, then he should know, after W, that this event sigma will keep him in a safe state. Okay? So now, as I said at the beginning, sometimes there is not, these conditions of controllability and observability are not met by the system and the goal behavior that we consider. So in that case, we cannot realize exactly the goal behavior K. But still, we would want to realize as much as possible of this goal behavior. We would want to stay within this goal behavior. So for this, we define the notion of safe supervisor. The supervisor such that the control behavior by this supervisor is within the set of words K. And it's maximally safe if there is no other P supervisor which stays also within the goal behavior and which is larger than the behavior of the maximally safe supervisor F. And we can, in fact, synthesize a maximally safe supervisor, P supervisor, in case the set of controllable events is included in the set of observable events. And this maximally safe supervisor is defined as follows. So it says that after the sequence of event W, sigma is not disabled by the supervisor, if only if the supervisor knows that after sigma and after any any sequence of uncontrollable events, the system is still in a safe state. Okay. And we have a necessary and sufficient condition for the existence of P supervisor, which corresponds to the fact that this formula should hold. Yes, I forgot to mention that this formula must hold. That initially, the supervisor should know that after any finite sequence of uncontrollable events, the system is in a safe state. Okay, and this condition is necessary and sufficient to have the existence of a maximally safe supervisor. So now we move to the to infinite games, and we deal with the second embedding from infinite games to supervisory control theory. So we have just embedded supervisory control theory in epistemic temporal logic, and now we're going to embed infinite games in supervisory control theory, and then we'll get our final embedding in the third part. So first we need to extend the theory of supervisory control to the infinite setting, because as you could observe, supervisory control theory deals with finite behaviors, but now we need to deal with infinite behaviors, and in that case we define the infinite Gore behavior associated to a formula chi as follows. So first we define it in the finite case. It's just a set of words which satisfy chi. And then we extend it to the infinite case by just taking a kind of closure and saying that that's all the words, infinite words, such that all the finite prefixes belong to this set. And then we define the notion of infinite supervisor as a supervisor which is never ending. That's the meaning of this condition. It says that as long as you follow a path which is recommended by this supervisor F, then there will be an extension of this path which is infinite. That's what this condition says, basically. And which will stay within the supervised behavior, the control behavior. So we can, in this setting, synthesize a maximally safe infinite P supervisor in case a condition is fulfilled, which is this one. So if this condition holds, then we can synthesize a maximally safe infinite P supervisor. What does this condition say? It says that as long as you know that after any finite sequence of uncontrollable events you are in a safe state, then there exists a continuation of the current state you are in, such that at any time in this continuation you know that after any finite sequence of uncontrollable events you are still in a safe state. Okay, that makes sense. And if this condition is fulfilled, then we can synthesize a maximally safe infinite P supervisor. And it takes all the uncontrollable events plus the controllable events, such that he knows that after these controllable events and after any finite sequence of uncontrollable events, he is still in a safe state. And this condition here turns out to be a necessary and sufficient condition to realize this Gore behavior here. So now we're going to embed infinite games into this infinite extension of supervisory control theory. Yes?
So this is the only place where I've seen the quantifier, the path quantifier being used. Is there any other place?
Sorry?
Yeah. Is there any other place where you need the path quantifier? And the other thing is that
You mean if there is another formula where...
in any of your codings,
yeah.
that's a very powerful thing.
Yeah, I know. No, I think that's the only place. And that's why you need...
Here you're using it like CTL. I mean, it's really it's box, right?
Yeah, no, but there is no universal quantifier here. That's why I need CTL star, because there is no quantifier here. But that's only for this, right? Otherwise, I could use. I think I could.
I mean, there is an implicit for all quantifier.
No. There is no for all here.
I mean, how do you interpret I as 0?
So it's for all the runs.
So it's a for all.
Yes, but it's not within the bracket. The for.
It's outside.
Yeah, of course. But I use CTL star because I don't want the for all here in the bracket. Okay.
In CTL, you don't have the quantifier in the bracket. Because this, okay, it seems to me that the formula, the first argument of the anti here, can be thought of as state formula.
No, I don't think so. No, it's not a state formula because it depends on the path in which you're in the history that you have played. It's not a state formula. This is not a state formula.
Safe is exists. There exists a path to cry.
Yes, but safe
Safe
is
is a state formula.
yes, it's a state formula. Yes, safe. Yeah. But this K you see, safe is not a state formula.
Why? I mean, it says that.
Because it depends, here you have until here, so it...
No, but I mean, just inside.
Yeah.
It's a state. Just the first argument of the until is a state formula.
No, it depends on the sequence of events that has occurred.
No, I mean, it's something that you evaluate from point.
No, you don't evaluate in the point, you evaluate on the path.
No, but the past is, I mean, it's a point in the unfolding of the tree, but it's a node. It's not a future branch that you evaluate. It's just on a node. The past has nothing to do with it.
Yes, it has to do. The past is important here.
Whether it's a state formula or not. Past doesn't.
Because you don't need the future to evaluate it.
You don't need the future. This is what it's a state formula. State formula is about future.
Yeah.
The past formula, sorry. So I think this is written in maybe CTL. I don't know. Now that John has.
Okay, maybe we can take it offline. Yes. So I'll first recall the setting of infinite games. So a game structure is a graph where the transition function is non-deterministic. Delta is the transition function, and you have a set of observations, and each of these states is labeled via the observation function by a unique observation from O via this gamma function. And a play is an infinite sequence of states and events sigma, such that for all Li sigma 1 Li plus 1, this tuple belongs to the transition function. So we denote by place the infinite place, and by prefix of j the finite prefix of this place. And a strategy is a function which takes a finite prefix of a play and yields an event of the set of events sigma. And it's observation based if in case the observation sequence of two finite prefixes are the same, then the event recommended by the strategy alpha is also the same. And the outcomes of the game following strategy alpha are all the plays induced by the strategy alpha. Then we define target observations, and we define two objectives, reachability and safety, but here we only consider safety. A safety objective is just a sequence, a set of plays, such that all the states which are visited by this play belongs to the target observations. And we say that the strategy is winning if all the set of plays, if all the plays induced by these strategies stays actually within this safety objective. Okay. And now we can set some informal connection between these different concepts. So the game structure can be mapped to a plant. A play of infinite games can be mapped to a trace. The safety objective can be mapped to the Gore behavior. The strategy can be mapped to a supervisor. Observation-based strategy can be mapped to an infinite P supervisor. Winning strategy can be mapped to safe supervisor. And outcome of strategies can be mapped to a behavior or the control behavior of the plant by the supervisor F. So as you can see, I only talk about safe supervisor. I do not talk about maximally safe supervisor, because the point is that this maximally safe supervisor will allow us to build all the winning strategies. So for this, we first need to make a bit more precise this informal connection between game theory and supervisory control theory. And we need to embed formally and rigorously these different notions. So here is how the game structure is embedded into a plant. So as I said, in a game structure, the transition is non-deterministic. And how are we going to make it deterministic? We first, so we just somehow collapse this sigma and this observation into one event, sigma observation. And all the other states which are reachable by this sigma and which yield the same observation, they are just reached in the plant by adding unobservable events. All these are unobservable events. So you can go from here to here, for example, by first going through this transition, and then, which is an observable transition, and then you take an unobservable transition and you reach this state. And you do this for all the different observations that you can reach after the event sigma, and you get like chunks of states like this. And this way we have a deterministic transition system. From place to trace, it's rather natural, so I will not go through the details, even if it looks a bit complex from a formal point of view. And from supervisor to strategies, so how do we associate a supervisor to a strategy? So we take all the uncontrollable events plus the pair alpha of pi, where alpha is the strategy of player 1 and pi is the finite prefix associated to the word W, and O is an observation. And back from P supervisor to strategies, and in that case, as you could notice, that the P supervisor are not deterministic, so you will get a set of strategies which are defined such that the event which is recommended by this strategy belongs to a set of events which were not disabled by the supervisor. And now we have the bridge theorem, which makes the connection between game structures and plans, and strategies and supervisor. So this goes from games to plans, and to go back from plans to games, then in that case we need to take the union on all the strategies which are defined by a supervisor. Okay. And in that case, the supervisor F is maximal. Then we will be able to get all the strategies, later on all the winning strategies, because of the maximality of the supervisor. So now we go from objectives to goal behavior, and what this shows, this purposes, is that the kind of goal behavior, infinite goal behavior that we considered are actually safety objectives. Because we can always extend the evaluation of the overall environment with the proportional variable p chi, so that the infinite goal behavior that we saw before is equal to a safety objective, which is which consists of all the infinite words which satisfy p all the way along, this new proportional letter p. So now we are ready to state our main results. First, I will start with imperfect information games. So the first result bridges the three frameworks that we considered: game theory, supervisory control theory, and epistemic temporal logic. The first one says that the strategy is winning for a safety objective if only if the supervisor, the P supervisor associated to this strategy is safe for the infinite goal behavior, if only if, and that's the interesting part, at any time and for any play induced by this strategy, the supervisor knows that he's in a safe state. Okay? So the strategy is winning if only if, for all the plays induced by the strategy, and at any time during these plays, the supervisor knows that he's in a safe state. The second theorem is about the existence of observation-based winning strategies. So player 1 has an observation-based winning strategy for a safety objective, if and only if, as long as he knows that he's in a safe state, then there is an extension of this current run such that at any time he knows that it's in a safe state. And as corollary, because of the complexity that we had about our epistemic temporal logic, this problem is in exponential, is in time. The second result is about the synthesis of the winning strategy. So we have first assumed that he has indeed a winning strategy, which corresponds to this condition here. Then the strategy is winning for the safety objective, if only if for all the plays induced by these strategies and for all finite prefix of these plays, after this, the last event of the finite prefix, an event sigma is recommended by a winning strategy if only if he knows that after this event sigma, he knows that he's in a safe state. Okay? So, in practice, how can we use this result? Then we take a finite play, a finite prefix of a play induced by a strategy. So, and we want to decide which are the events that we can play. So we take an arbitrary event sigma, we put it here, sigma, and we model check with the finite play that we have just reached. However, after this finite play, this finite prefix of the play, we know, the supervisor knows that after sigma, he knows that he's in a safe state. Okay? So, and this way, we are sure to stay within a winning strategy. Okay? So this gives you a way to synthesize all the winning strategies. So you start first, you first consider the first event. Is it possible to play this event? I just put this event here and I check initially whether I know that after this event I know that I'm in a safe state. Then I move to the second state, and I consider a second event. Am I allowed to play this second event? Then I put the second event here and I model check again whether I know that after the second event I know that I'm in a safe state, and so on. That's why it's I call it on-the-fly generation of winning strategies. Because you do it incrementally, event after event. You build your strategy, your winning strategy, event after event. And this, the problem of constructing this winning strategy is exponential in time. That is, but yeah, it's not. We don't know if it's optimal yet. And the result, relating more closely the infinite games with the notion of controllability and observability is the following. It says that in case the system satisfies these two conditions, which were, as you can recall, the notions of controllability and observability, then it is possible to fully realize the safety objective, because that is, we'll have at our disposal a set of strategies such that if we take the union of the plays induced by this strategy, they will coincide exactly with the safety objective, whereas usually it's just an inclusion in this order. So it's a side result. And for the setting of perfect information games, then the results are exactly the same. So we can again map the framework of game theory, supervisory control theory, and epistemic temporal logic by this theorem. So the result is the same. The strategy is winning for the safety objective, if only if for each play induced by this strategy, at any time, the system is in a safe state. And for the existence of winning strategies, it's also the same. we just remove the knowledge operator, but we get the same formulas without the knowledge operator. And in that case, player 1 has a winning strategy for a safety objective if only if, as long as the system is in a safe state, there exists a continuation of the current state, such that at any time the system is in a safe state. So we do not need to build all the winning states. We just need to model check whether this formula here holds in a specific state. So I took S0, but it could be actually any state of the environment. And it turns out that in that case, the problem of deciding this is decidable in linear time. Likewise, for synthesizing the winning strategies, we just remove the knowledge operator. And in that case, the strategy is winning if only if, for all the finite prefixes of the plays used by this strategy, it holds that an event is recommended by a strategy, by this strategy, when after this event, and after any finite sequence of uncontrollable events, the system is still in a finite safe state. And in that, so here again, you have a way to synthesize all the winning strategies on the fly. That is, after a sequence of events, I can decide whether or not I can play an event, and this event will stay within a winning strategy. And we have again similar results to realize exactly the runs of the safety objectives, in case the condition of controllability holds. So, our contributions are as follows. We cannot determine whether there exists a winning strategy in a specific state without having to compute all the winning states. We can just do some model checking and check whether a formula holds in this state, and in that case we know that there is a winning strategy. Moreover, we can synthesize all the winning strategies, not only one of them, but all the winning strategies. And the way we synthesize them is on the fly. That is, we have a way to build them incrementally, step by step, by checking whether a specific formula holds in the system, and if this formula holds, then we can play this event, and it will stay within a winning strategy. And our formulation highlights the main underlying intuitions, because as you could see, the formulas of epistemic temporal logic, they make sense. And they are all expressed, all our results are expressed in terms of model checking problems of epistemic temporal logic. That means that we can use the model checkers of epistemic temporal logic, such as MCMS or MCK, to implement these results, and this may ease the applicability of our results towards applications. Thank you.